In this video, we're going to learn about techniques to reconfigure high-speed PCBs so that you can inspect signals without disrupting them. This video is inspired by a technique that works well at low frequencies but causes tremendous grief at high frequencies. Here which is connecting a test point to a wire. Here I've shown two chips attached to a transmission line, one of which is sending a signal to another, and for some reason we think this signal is interesting and we'd like to inspect it off chip, so we've attached a test point connector to it. However, if we make a circuit model of this situation, then we see that this off-chip inspection is really problematic. The transmission line leaving the transmitter sees two transmission lines at the T-junction, which results in a large impedance mismatch. And even if we custom designed the traces to act like a splitter, so made the Z0 for the load and the instrument double-sized, which might cause mismatches at the instrument or the load, we still have the issue of splitting the power in half. Even worse, if we ever disconnect our instrument, like we inspect this signal and decide it's okay, then Z instrument becomes an open circuit, which leaves a really nasty stub in our circuit. We have this trace that runs out and reflects off an open circuit and comes back into the middle of our transmission line. We can fix this using components called 0-ohm resistors as a replacement for jumper connectors. Because you can hook surface mount components onto a transmission line without disrupting the characteristic impedance too much, and because we can make resistors that have extremely low resistance, basically 0 ohms, you can just solder a resistor in line with your transmission line without disrupting your signal too much. And by switching that transistor between a forward path or an instrument path, we have the ability to reconfigure our circuit without any impedance mismatch issues. 0-ohm resistors can provide lots of types of configurability to high-frequency systems, allowing you to connect and disconnect amplifier chains in addition to tapping out signals. And they'll do this all without introducing the parasitics that you get off of jumper pins or discrete switches, which are notoriously bad in my experience. Now, as an aside or an alternative, if you really needed to watch this signal live, so you needed both chips operating and still wanted to watch the signal, you could build a directional coupler in order to tap off a little bit of energy out to your instrument. However, that's a pretty high design complexity debugging technique. It's good that 0-ohm resistors work well because probing RF systems is difficult. Near-field probes can give us some information without contacting traces, and they're relatively easy to use, but you're just measuring kind of often frequency domain representations of voltages and signals, and so you don't get senses of switching times or modulation out of near-field probes particularly easily. However, contact probes are really pretty limited in RF systems. When you think about using a contact probe with an oscilloscope at low frequency, the probe usually has a very high impedance, which means that relatively little RF energy is going to flow into the probe, because they'll have a big impedance mismatch with an RF system. So they won't disrupt your system too much necessarily, but they also won't pick up much power, so you won't see a signal. If you do manage to design a probe and oscilloscope input that is 50 ohms, you can pull signals off of your board, but then you have the same problem as a instrument connector where you're putting kind of weird terminations on existing transmission lines. So in summary, connecting equipment without thinking about it can cause reflections by messing up your trace impedance or adding extra loads. 0-ohm resistors let you get around that by reconfiguring connections with low parasitics. And near-field probes are easy to use, but give you limited information. Contact probes are much harder to use in RF systems.